Okay, so hello and welcome. Today we are going to talk about uh, the pseudo forces in rotating frame, or else it's just motion in rotating frame. So we are having some motion in the lap frame, and then there is a frame rotating. So let's say this is our S frame, lap frame, and for the simplification, right now I will be rotation will be along. So for the simplification, rotation will be along plus Z axis. Okay, but while deriving it, I will generalize this for the general omega vector. Okay, so this is my x and y here, and when the frame, let's say we have another frame, okay, which is rotating. So at any particular moment for the x prime and y prime, for this angle, we have this rotating frame, this x prime y prime. So if you look at this frame of reference at different times, so this axis will move here. So this line and this I mean this these axes will rotate. Okay, so that is the picture here. So the thing is that we are watching some, let's say, some position of a particle. So let's say this is a particle P having its some trajectory here, right? It can have a trajectory. So let's say the position vector is R vector in S frame, and since we are going to discuss, our basic aim is to trace trace out trace out the trajectory of particle in rotating S prime frame. So this is our basic aim here. Okay, this is the basic aim. So we know that R vector is equal to xi and ei. So what is xi here? Just if I expand this, it will be x e1 plus y e2 plus z e3, correct? So z is out of the plane here, and this uh, s prime frame is rotating along this z. Okay, so axis is fixed along z, and then it is rotating, right? So this we know. Now we can also write this r vector as something in the prime frame. So e1 plus y prime e2 plus z prime e3 prime, right? Everything prime, but the vector is unchanged in the prime and the unprime frame. So that is very important statement here, that the vector doesn't change. Even if you change the coordinate system, vector doesn't change. So that is the underlying thing here. Okay, so if we agree on this, then what we can do is we can write r vector here. So we start from this particular equation and writing it in the condensed form. So we start with this equation here. Let us write this thing as x prime I and e prime I here, where the summation is on I. So whenever there is a repeated index, we assume that there is a summation, which is the Einstein summation index, or explicitly you can write I here from 1 to 3. But I will not do this summation thing here. It is assumed that the repeated index are summed over. So let's talk about the velocity of the particle, right? So this is the position vector in the prime frame. So this is in the prime frame, right? So let us differentiate this equation, dr by dt, d by dt here, x prime I, e prime I vector. So basically dr by dt here in the unprimed frame, if we expand this r in unprimed frame, so this is u vector, and in the non-rotating frame or unrotating frame, so let's write unrotating. So ur is the unrotating frame, right? And then there is a d by dt here. So you see that this x prime I, what is x prime I? So x prime I is something, if I just make this, so let's say this is my x prime and this is my y prime. So at some particular point, this is my x prime, this is my y. So this particular thing is x prime and this is y prime. and as the particle moves along, this x prime and y prime are going to change, so that's why they are function of time. Now what about this e prime I? See, e prime I is also a function of time. Why? Because as the time goes on, this x prime and the y prime axis, these arrows, they shift. So at one particular time they are here, now at some other time, let's say, let me change the color. So at another time it will be x prime at some time t2, and then this will be y prime at time t2. So you see that the basis vector is along this direction, right? So this basis vector themselves are the function of time. So that's why they both are function of time. So we have to use the product rule of differentiation here. So it will be simply, oh, let me change the color again. So it will be simply dx prime I by dt e prime I plus x prime I and d prime I by dt here. Okay, so what u in the unrotated frame is, so just look at this equation. This equation is what this equation is telling us is that in the prime frame, the coordinate change with respect to time and then expanded with the prime frame basis vector. So this is nothing but the velocity vector in the rotating frame. So this is ur. So this is the velocity of the particle in the rotating frame, very important quantity. And then x prime I and di prime by dt. So we have to really figure out this quantity in order to connect anything from here. We have to figure it out. So it is comparatively easy if we see how. So we see that we have to look for. So let me change the color. So now we have to look for the transformation laws of coordinates and basis vector. Right. So let us just write the, so in order to do this differentiation, we have to do that, right? So we can write the E prime 1, which is nothing but I prime cap in the more familiar notation, doesn't matter, is cos theta I cap plus sine theta, or rather, let me not use the I caps, cos theta E1 plus sine theta E2. So this is a transformation from the prime frame to the unprimed frame. How do we exactly see this? Again, if I make the diagram x, y, and then change the color, x prime, y prime. So we are looking at this particular vector. Again, change the color. So we are looking at this vector here, this particular vector. This is my E1 prime, and this angle is theta. Now what I am doing is I am just breaking the component form along the unprimed frame. So that is what cos theta E1, because this angle is theta. So cos theta E1 plus sin theta E2, and this also confirms that this vector is a unit vector, right? So again, change the color. So now what E2 is? So E2, what exactly is E2? If we look, so this vector here, this vector here, this is my E2 prime, right? So from here we see that there is a negative component in the x direction and the positive component in the y direction, which is minus sine theta E1 and plus cos theta E2. So we have these transformation laws here, even for even prime and E2 prime, right? Now what we can do, we can simply differentiate it, right? And then before even differentiating, we should expand this quantity here. Now let me switch to the green, because this was just diversion to continue the our original derivation. So this equation we have to use here. We will continue from this equation. So u, let me change the color to green. So u in unrotating frame is equals to u in rotating frame plus some quantity which is, if we look up, it is a sum on I. So it is x prime I e I, so we have to sum over I. So basically that is saying that x prime d 1 prime by dt plus y prime d e2 prime by dt plus z prime d e3 prime by dt, right? So here we continue writing. So now if we just differentiate d1 prime by dt, we observe that this e1 and e2, they are fixed vectors, so they are just uh, this direction and this direction. So this is my e1 and this is my e2, so they are fixed. Only the primes are the uh, function of time. So that's what the advantage. That's why we have transformed, so that we are able to differentiate. So if we differentiate this, it should be minus sine theta and d theta over dt. But if we say that theta is equal to omega t, right? So theta is changing with omega. Now this omega can be a function of time. Okay, so this omega can be a function of time, but d theta over dt, if we took it to be omega as a function of time, let's say, so then it will be d1 prime by dt would be, if you observe, it would be simply omega times e2 prime, right? That is not very hard to see here. So it will be x prime omega e2 prime here, right? And plus y prime omega. Now if you differentiate the e2 prime, it will be minus of minus omega times e1 prime, which you can see very easily. So you have to replace this with a minus y prime omega and e1 prime. Now the z-axis, assume them like they are coinciding, so it would be simply d z here and d e3 prime over dt, because the e3 prime, so e3 prime here is equal to e3 because they are overlapping. So anyways, e3 is not changing, hence this is just 0. So not, the last term doesn't contribute. So this goes to basically 0. So the unrotating frame is equal to this rotating frame plus. Now we have these strange looking quantities, right? But they are not, they're easy to interpret if you think about them in, I mean, if you think in terms of the cross products here. So if you think in terms of the cross product, they are very, familiar quantities. So let us see let us wonder like what exactly is R cross omega. Okay, let us just wonder what is R cross, what should be R cross omega, right? So if I express R in the primed basis, so R in the primed basis, so we can write this as the determinant of e1 prime, e2 prime, e3 prime. Remember how we take the cross products, right? Z prime, and then omega, I have assumed that omega is along the Z, so 0, 0, omega. That is how we are doing here. So if we see what is R cross omega, it would be just e1 prime and y prime omega and minus e2 prime, simple algebra, x prime omega. So from here we see what is this quantity, what is the correspondence between these two quantities here, this quantity and this quantity, right? So if you see, only one minus sign difference is there, which we can incorporate by changing the order of this cross product. So I am simply writing u unrotating u, that is particle velocity in the non-rotating frame, plus particle velocity is equal to particle velocity in the rotating frame, plus simply the reverse of this cross product, so omega cross r. Okay, so far so good. So we have come to the equation which connects the velocity in the non-rotating frame with the velocity in the rotating frame, and the connection is led by this omega vector. So from here, just a quick check, if omega is equal to 0, which means frame is static, non-rotating. So if the frame is not rotating, the unrotating frame particle velocity is equal to the rotating frame. So this quick check yields correct answer. Okay, so we'll accept that. And now the most, so velocity is one thing, but remember that the Newton's laws of equation, the Newton laws of motion is formulated in terms of the acceleration. So Newton's second law tells us that F is equal to ma, right? So forces gives the acceleration. So you have to see how does the acceleration changes, and then from the acceleration we can figure out the forces that acts on the particle in a rotating frame. So that is our goal here. So let's again change the color. So just I mean to derive the acceleration, just differentiate. So differentiating this equation number one with respect to time. So du unrotating by dt dy, sorry, this should be equal here. So d by dt. So this is, I'm differentiating the particle velocity in the rotating frame with respect to time, plus d omega by dt. So here I'm just applying the product rule, omega cross dr by dt, right? So what this should be, so basically we have to expand this thing again in order to differentiate it. So this is particle velocity in the rotating frame, right? But the particle velocity in the rotating frame is equal to something like it was x prime I, or rather let's say, let us write it in terms of velocity components only. So because it is in the rotating frame, though, the primed velocity component and then the basis vector, right, in the prime frame. That's why in the rotating frame, that's why it makes sense. Okay, and then we can write this one as omega cross omega dot cross r. So this term here is there because if let's say my omega is not fixed, if there is no constant angular velocity, but the angular velocity itself changes with time, so that's why we have this term here. And then this one here is dr by dt. So dr by dt is simply the uh, particle's velocity in the unrotating frame, right? So just to keep these terms untouched here, let us not touch these terms and evaluate this term, and then we look for the final expression. So this one here would tell us that it will be d by dt u prime I e prime, again applying the product rule, u prime I and d I prime by dt, right? And plus let us leave everything here in a single bracket. So there is a single bracket here which represents this particular expression. So what is this first quantity? How do we identify this first quantity? So this is the derivative of ith component of the velocity with respect to time and expanded over the new primed basis vector. So this is nothing but the acceleration in the rotating frame. And what should be the LHS? So LHS is just acceleration in the non-rotating frame, right? Acceleration in the non-rotating frame is equal to acceleration rotating frame, this quantity, but plus u prime I. So again, if we expand this, so this will be u prime x, right? If we expand, so de1 prime by dt plus u prime y de2 prime by dt, and the last term d3 prime by dt will be 0 because again the z-axis is not changing at all, so that it would contribute to nothing, and plus these brackets. Okay, so we have to solve the first term is sorted because this is the acceleration in rotating frame. Second term we have to again solve. So acceleration in the of the particle in the non-rotating frame is equal to acceleration of the particle in the rotating frame plus this quantity here. So again, we just use the above expression u prime x, and this should be d1 prime by dt. So what was that quantity? So it was simply omega e2 prime, right? And minus u prime y omega e1 prime. Yeah, and then this particular quantity here. Let us just leave it there. So again, we want to write this in terms of a cross product because this seems to be a cross product. So let's just see what the omega cross u in the rotating frame is. Right. So when I write the rotating frame, I simply mean that u vector I am expanding something like sorry, u prime I and e I prime, yeah, vector, right, in the prime frame. So that is what is meant by the rotating frame u, right? So here if you see in the rotating frame, I'm choosing the prime basis vectors, and because first I'm choosing it to be omega and the second one would be ux prime, ui prime and uz prime. So what this will be even prime and hide this thing. So it will be uh, minus omega uy prime and sorry minus e2 prime, this will be minus omega ux prime. But then we see that this expression here again, this expression is exactly equal to this expression, right? If we check, then it comes about right thing. So basically this quantity here is nothing but omega cross u, where u is in the rotating field. So we can write that. Okay, so acceleration in the unrotating acceleration of the particle in the rotating frame is equal to acceleration of the particle in the rotating frame plus this one here is simply omega cross u in the rotating frame and plus the last. So let us just pull out this bracket, open this bracket. So it is omega dot cross r, and there is a omega cross u but in the unrotating frame, right? So here we want to express this quantity here in the unrotating frame as a function of velocity in the rotating frame, right? Because we want to equate LHS RHS, so here are the all the unrotating things and here should be the rotating things, and basically we want everything, I mean we want to express this rotating frame thing with respect to. So what I'm saying is that we cannot like pull out this thing to the left hand side, right? Because then we are having mixed terms, but we just want rotating and unrotating separately. So we want to express the rotating frame thing in terms of the unrotating frame and then the quantities which are measured with respect to the rotating frame, right? We don't want to rely on the unrotating frame now. That's why we should express this thing as a function of the rotating frame. So we have, it is not a very difficult task because we already have the expression from here, where from this red equation we have that. So it will be ur plus omega cross r. So it is not that difficult. It turns out to be not that difficult. So it is a r plus omega. So basically, if we just expand this, so there will be two terms omega cross ur, and omega cross ur is already there. So it will be 2 times omega cross ur plus omega dot cross r plus omega cross r. So we have three terms here, one, two, three, and this is acceleration rotating frame. This is acceleration of the particle in the unrotating frame. Now the simple thing, final expression is that the acceleration of the particle in the rotating frame is equal to the acceleration of the particle in the non-rotating frame, but we have to minus these three terms. So it is minus 2 times omega cross u as measured in the rotating frame minus omega dot r minus omega cross r. So these three forces, 1, 2, and 3, these possess three different names. They are all the pseudo forces, right? So this first particular force, this is what we refer to as Coriolis force. This thing here, because this thing here, it depends only if the angular velocity is changing with time. So this is Euler force, and this thing here is recognized as the centrifugal force. So Coriolis force, Euler force, and the centrifugal force, all forces at once, right? So to just to simply ease out the case and then explain whether these expressions are correct or not, just to check. So let us just demonstrate it with a very simple example of, let's say there is a point O fix, and then you have a stone here. So this is a stone, and this stone goes round and round. Okay, and goes round and round with a fixed angular velocity. So this moves with the angular velocity omega. So this means that the Euler force is equal to 0 because no change in angular velocity. Euler force straight away goes to 0. And now assume a rotating frame like this, and this frame is rotating. So this is x prime y prime at t is equal to 0, and then this frame is rotating like this with center at origin. So in this frame, the particle will be at rest. So the particle won't possess any velocity, right? So which means that in this particular example, the Coriolis force will also be equal to 0. So what remains is the centrifugal. So you cannot go, eliminate the centrifugal force at any cost, right? Because it is a very basic thing. It is a very basic force in the rotating frame, and it only depends on the omega. So if omega is there, I mean, if the frame is rotating, centrifugal force has to be there. So let us calculate the centrifugal force. So centrifugal force is minus omega omega cross r, right? So this thing here, if we apply the product rule, cross product rule, so it will be omega omega dot r, everything is minus, right? And plus r and omega square, right? So here, to further simplify, because the omega vector is in this direction, this is our omega vector in the z direction, and we are watching this r, this position vector r, right? This is perpendicular, so this is in the x coordinate and omega is in the z direction. So omega dot r is 0. The only term survives, which is this one. So what does this term suggest? So basically this gives you the centrifugal force of FCG, centrifuge. Well, okay, fine. FCG is r omega square. So what does this suggest actually? So at any particular r vector, if you see, the centrifugal force is in this direction. So this is FCG. So if we make the free body diagram, in the rotating frame, so FBD in rotating frame, so what do we see here? So we see that there is a particle which is experiencing a force here of FCG. This is centrifugal, but then there is also a force of tension here, right? So we just use this equation. So what is the acceleration in the rotating frame? Or if you multiply everything with mass, ma becomes the force, right? So the rotating frame force is equal to x, ma. So let me just write that expression in the force force, using the force picture. So F force in the rotating frame is equal to force in the, force in the unrotating frame, and plus F of Coriolis, plus F of Euler, and plus F of CG. So in our case, in our simple case, Coriolis and Euler force were 0, only CG remains. So the rotating force will be unrotating. So the unrotating force is in this direction, which is just the tension in the rope. So it will be, let us assume that this is just any direction n cap. So let us write T is in the n cap, so it will be T n cap, right? In the unrotating frame, only tension is there, right? And plus the FCG. So what is the FCG exactly? So FCG should be m times this quantity. So m times this. So m omega square r. M omega square r. Right? But in the rotating frame, from the intuition, we are claiming that the Fr should be equal to 0. So this Fr equals to 0 because the particle isn't moving. So because the stone is rotating at omega velocity and we are rotating along with the stone, so there is no way that we should see the stone accelerating. So the rotating force should be 0. So what does this mean? So this means that T minus T n cap should be equal to m omega square r. So is the tension equals to the omega square r? I mean, if it is it true? Is it true? Let us see. And here direction we have to see. So it should be here minus n cap, right? Minus n cap. So here this will be gone. Everything will be gone here, right? So the tension should be equal to m omega square r, but this is true because this is simply the mv square by r if you are more familiar with this particular form. So mv square by r is equal to tension is nothing but the centripetal force in the unrotating frame. So we have derived from the intuition that the tension should be equal to this, and without even considering, if we do not consider this particular equation or analysis, we know that tension is indeed equal to that particular quantity. So which means that our equations are indeed correct, right? So that is all about the Coriolis-Euler centrifugal force. So one thing which I want to show to you here is that I just want to show you the Coriolis force in action. So for that I want to open YouTube. Let us see. So Coriolis force. So there is a video of Harvard people. Yeah. So if you see this video here, there is an ad. Yeah. So these people are moving along this rod. So there is a rod, and the two persons are sitting at the end points of the rod. So there is a seat here. This is a seat, and then they are going to throw ball at each other. So we are interested in the trajectory of the ball as observed in the rotating frame. So you see that they are trying to give the velocity of ball towards the person at the opposite end, but the ball curves as seen in this rotating frame. So you see that the ball actually curves. So this curving is there because of the presence of centrifugal and the Coriolis force. So basically the curving motion is there because of the because of the Coriolis force. So I have designed one simulation for the same. Let us look this same situation and discuss in the video and in the simulation here. So here if you see that in the lab frame, this ball is being thrown in this direction. So in the lap frame, there is no reason that ball should curve, right? If it is being thrown in this particular x direction, then it will sail away with the same velocity, right? But in the rotating frame, as you saw in the video, when if I put the Coriolis force and centrifugal force and then integrate for the part trajectory, so we get this particular form. So I've used one code of using RK4 method to integrate this trajectory, and then we get this type of trajectory here. So maybe I can just zoom out and then show you how it exactly moves. And this one here, it just, I mean, this just goes, sails away with the same velocity because there is no acceleration, there is no force on this ball, right? I've just, neglect gravity. I'm not taken gravity into the account just to simplify things. But here, if you see, yeah, this is the trajectory of the ball as observed in the rotating frame, and it curves like that. Okay, I think that is it for today. See you in the next video.